One of my absolute favorite data tools is pandas. It's incredibly flexible, and while it does have some inconsistencies in its API, it does have a coherent design. But I'm not here to just talk about pandas today. Today I'm going to also be talking about the newest DataFrame tool on the open source market, polars. Specifically, we're going to cover some of the core mental models of both pandas and polars, where they converge or align and where they differ, and how you can make the best use of both of these tools depending on the task that you have at hand. But first, as I mentioned, today we're going to be covering both polars and pandas. What is it that makes them tick? Why do we need two tools? And I'm not even going to mention the litany of other DataFrame-like tools or tabular tools that we have available to us. But there are some key underlying concepts that you need to understand if you want to make the best use of pandas, as well as the best use of polars. We have polars, we have pandas, they both have their own DataFrame import. They look exactly the same. When I go ahead and run this code cell, let's take a look at the output. Well, I can tell that they both represent my data quite similarly, and maybe this representation, pandas, is a little bit more condensed, but I do like that polars gives you the data types out with its columns. But what's the difference here? Why does the representation really matter that much? Well, not really. What we can do with our pandas data frame, we can actually just take the value 2 and we can add it to our entire data frame. And this works exactly as we think it should. Oh wait, it doesn't. And that's because we have a string data type column. And pandas sees this integer 2 and it can add 2 to all of our integer or float data type columns, but it doesn't know what to do with this string type column, and that's why we get this type error here. Well, of course, we're all familiar or slightly familiar with polars, and we know that it's very strongly data typed across the columns. And when we add 2 to our data frame in polars, it's kind of strange. Everything got upcasted to a string. I mean, I've heard pandas upcasting things to floats unnecessarily, but upcasting to strings seems kind of odd here. And so what is it that makes polar tick? Why did this happen? Well, the first rule of working with polars is that if you treat it like a pandas data frame, or you try to use it like you would use a pandas data frame, things aren't going to work how you expect them to. Instead, you need to abide by polars rules, which are the use of a context and the use of expressions. And here we can see I get that nice error message that I was expecting when trying to add an integer onto a non-numeric data typed column. But let's go ahead and talk about this a little bit more. First and foremost, polars is not pandas, pandas is not polars, and you should use both of these tools according to their own rules and their own APIs. However, they are similar in that both polars and pandas are restricted computation domains. They are human interfaces that you can perform computations within in an expressive way. So, in pandas, I can write something like DataFrame plus 2, and what this is actually doing under the hood is using NumPy to operate at an extremely fast level, a level that is not achievable just using Python. Polars has this same notion, this same idea. And whenever we're working in a restricted computation domain, the most important rule is you do not want to cross back and forth across that restricted computation domain boundary. So, the one thing that we know about pandas from Don't Use This Code is that pandas is all about the index. Well, there's a little bit more to it, but pandas really loves its index. And so if I take two data frames and I'll go ahead and create them, they each have their own index, they have their own columns, and you can see that my top data frame, or df1 here, has columns w, x, y, and z, and rows a, b, c, and df2 is slightly dissimilar, but they do overlap. They do both have rows a and b, and they both have columns y and z. Well, in pandas, I can actually operate on both these data frames. If I just want to add everything that these data frames have in common, I can simply use the addition operator. And you can see that I get a lot of nans out here, Well, the nans are actually from where these two data frames did not align, and I can prove that to you just by using a quick DataFrame.align. You can see that we took the union of all of the columns from both data frames, and then we re-indexed the data frame by its columns and its rows based on those unions. And you can see that my top data frame, it didn't have a U or V column, so all of these values are nan, and it didn't have a row named D or labeled D, so we have nans across all these rows. Now when we perform addition, all we're doing is aligning the shape of these two things, and since we're adding with nan for most of these things, we actually get null values back out, and then we only receive values in our top right quadrant here. Another thing that we could do is if we wanted to circumvent most of these nans, we could actually have an alignment fill value here, and then we could perform our addition in this way instead. This is just a little bit of Pandas API really stretching and letting you do what the operations that you want to do when you abide by the use of its index. Now, if Pandas is about the index, then what is Polars about? Well, Polars is all about lazily evaluated expressions and the context that those expressions live in. And I'll show you. If I have two data frames that are the exact same, right, as we saw above, just not Pandas data frames, these are Polars data frames, and I wanted to perform that same operation. I wanted to add these two data frames. What we can see is that when I just add these two things, well, I get a result out, and that's part of the way there. But if I look carefully at this result, I'm not lining up column W with any other column W. I'm not lining up column Y with any other column Y. What's happening here is we're actually relying on the shape of these tables. And so column W is just being aligned with the first column in my second data frame, and then we're performing an addition there. And what happens when we do this is simply relying on the shape of our data frame gives us a little insight about what Polars table manipulations are, and that Polars, the column names, are really just a human tag. This is us to identify pieces of information within our table. They're not semantic. Like in Pandas, we have index alignment giving semantic meaning to both our rows and our columns. Similarly, if I instead invert my addition operation, instead of df1 plus df2, I do df2 plus df1, we see that my output has different column names. I now have U and V instead of W and X. So what if I actually wanted to perform the same operation that we saw above, but in Polars? Well, I would need to concatenate these two data frames. Maybe I want to stick them on top of each other, just like we would do with a Pandas concat. But you can see here, okay, well, we can't vertically stack or concatenate these things because, well, column names now don't match up. So sometimes Polars does care about the column names, but not all the time. Okay, well, maybe I'm just using the wrong type of concatenation. I don't want a vertical concatenation. What I actually want is referred to as a diagonal concatenation. And what this is saying is this is essentially a vertical stack that's an outer join. So we're taking the columns that we have shared across the two things, and we are vertically stacking them. So my Y, Z, and index are all shared column names, and I actually vertically stack those. WX exists on the left-hand side in my data frame 1, and UV exists on the right-hand side. And so where those things don't align, we're just getting nulls. From here, it's actually a fairly straightforward group by reduction. I group by my index column, and then I perform an aggregation across the rest of the columns, and I do my sum. And then I can sort index, or I could do a maintain order for my group by, but we get the same result back. Now, this is 3 lines of Polars code compared to one addition operation in Pandas, and that's because these tools abide by different rules and they serve slightly different purposes. And so what I can say about Pandas is that it's great at taking many different data sets with similar structures, not necessarily the exact same, and combining or reducing or manipulating, wrangling, whatever verb you want to use for data. Pandas can usually serve you right. Polars does make it harder to write naive code that performs poorly, and this is one of its greatest strengths. The code that I write in Polars is typically going to operate extremely, extremely quickly compared to Pandas. In Pandas, it's very easy to take a naive code approach and actually have something that performs maybe even worse than pure Python. But in Polars, This is not impossible to do. You can still write bad polars code. However, I will say it is just much harder to write bad polars code than it is to write bad pandas code. If I take that same example that we were just examining, just looking at, and I approach it from a different way, instead of actually performing a vertical or a diagonal concatenation and a group by in order to aggregate these values, what I'll actually do is I'll melt my top data frame. And when I actually melt this top data frame, you can see that, right, I go from a wide view to a long view. Well, after I melt them, I want to actually join on the melted df2 because then I can actually have my columns line up and perform an outer join there. And I have this result. So here are the values from df1 and here are the values from df2. And now I can actually perform my computation, which is adding together all the values of df1 and df2, and then abiding by, right, where they came from, or the columns. And I can do a little fill null here if I wanted to make sure my output didn't have nulls. Then, once I've melted everything, I've joined it, I've added them all together, I can actually just pivot right back to my original shape and reconstruct my, quote, index here and perform a sort on it. And I get the same result that I had with pandas. And here you can see I've done a melt, I joined with columns, final value, pivot, sort, all in what pandas did in one line of code. And I'm not going to say that polars is always more verbose than pandas because the inverse can be true. And especially saw here, I performed the same computation with 3 lines of polars code. But what this is trying to show you is that it's not impossible to write bad polars code. And here's why this polars code is bad. Polars will tend to revolve around the use of its lazy API. And I'll show you what this means. A lazy API, all this is doing is instead of actually performing computations, it's constructing an execution plan to perform computations. And I can look at this plan by converting my concrete data frames into lazy data frames. And so instead of actually performing the computations, instead of actually concatenating these two things and performing a group by ag, it's just going to devise a plan to do that. We can then ask polars to present this plan to us, and you saw me print that out, but I can actually also ask it to optimize this plan, and this is where the power of polars comes into play, because by using this lazy API, we can actually give polars a set of instructions that we want to do in any order, and polars will then analyze that plan and say, I think I could speed it up in this way, and this way, and this way. Instead of using projections, I can use fast projections. And there's so many different optimizations that polars can make for you. This is why it's hard to write bad polars code. But the reason that I said this below detail is actually bad polars code is because if I go to convert my data frames to lazy frames, oh man, there's no pivot operation in a polars lazy frame. We can think about why that might be. Polars is purely driven by its knowledge of the schema and the operations that you want to do on it. And the schema is just what columns do we have and what data types are they. When I want to pivot from a long format into a wide format, I'm making an uncertain amount of new columns with potentially uncertain data types, right? They might be downcastable into something that was not shared when they were all stacked on top of each other. For example, if in my long data frame, I had one group of data that was supposed to be strings and others that were supposed to be integers, should polars treat them all as integers or all as strings when we pivot them? Well, it's hard to tell. And since there's also a non-deterministic amount of columns that we're creating from our row-wise groups, polars can't optimize this. Polars cannot incorporate .pivot into its lazy API. And considering polars lazy API is really its best strength because that's what takes our naive code and makes it run faster and more efficiently, well, this is why we might not want to take this approach when solving this problem. So when you're trying to solve problems in polars and you want them to be efficient and effective, you need to make use of the lazy frames and of these expressions. So what is polars all about? Well, Polars is all about query plan construction, which we just covered, and optimization of that. This is its lazy API. This is strongly consists of its use of Polars expressions and context. Additionally, Polars is also all about strongly typed heterogeneous columns, as we've seen in most of these examples. So what are Polars expressions then? Well, we're going to line up some pandas syntax as well as some Polars syntax for you to see if we can get to the bottom of this. In pandas, if we want to select just a single column, we use square bracket notation. In Polars, we use .select and feed it a list of columns. But we don't actually rely just on the strings of the column names. We actually can wrap them in this call function that returns an expression type. And what we can do with this expression is we can actually perform pretty much any mathematical operation on it. Any NumPy ufunc will work with these expressions. So I can take this column value, this value, and multiply it by 10. This actually, just this part of my computation, or my code, actually hasn't run anything. All this is doing is saying, okay, when we actually run this plan, I'm going to select the value column and I'm going to multiply it by 10. And how does Polars know what the value column refers to? Well, we give it a context. I'm saying use this data frame, and in the context of this data frame, we're going to select something called value, a column named value. We're going to multiply it by 10. These are Polars expressions, this in here. And this is one of the key components of Polars that really, really differs from pandas. I'll show you one more thing before we get to a deeper discussion of context in Polars. In pandas, if I wanted to perform something like a group by mean, well, I can group by the group, select the column out that I want to perform my statistic on, and then say on that result, I want to perform a filter. Well, if I want to perform a filter on that specific result, I need to rely on something like passing a lambda into .lock, or I could use .pipe and then use a .lock there. How we pass around state in pandas is through the use of functions. All pandas cares about is, have you given me a function? And if you did, I'm going to pass myself into the function and become whatever it returns. The issue with just pure Python functions, even if I'm leveraging all of the speedups that pandas provides and I'm writing nice vectorized code, so to speak, well, functions are always black boxes. They're not transparent. That means at runtime, pandas doesn't know that I want to filter values greater than 20 until I actually ask it to. Meanwhile, Polars, on the other hand, if I wanted to perform this same computation, I would group by my group column, then I would pass it an expression to aggregate that group. I'm going to take the mean of all my values within each of those given groups. Then I'm going to filter for values greater than 20. If I lazily compute this and just show you the plan, you can actually see that before Polars even computes anything, it knows exactly which values it's going to use and where it's going to use them. This gives Polars an incredible amount of information to actually optimize this query plan and perform some very sped up computations. Additionally, we can do things like we can implement redundant operations. So if, again, I take this lazy data frame and I ask Polars to sort it based on the value, and then I ask it to select the maximum value from that column, well, one of the optimizations that Polars could do, and it's not doing it just yet, but since all I'm doing is taking the maximum column from this data frame, or from this column named value, we actually can omit the sort completely, unless I'm using that for something else later on in my query. So what composes this Polars context then? Well, if I take a static Polars expression, and all this is you can think of this exactly like a Python function, except all I'm doing is I'm saying, hey, at some point I'm going to take a column named value, I'm going to take the mean of it, and I'm going to rename that thing, rename that column. In pandas, we can achieve the same computation by creating a function, right? And in that function, we take the value column from the data frame and call .mean. And I could even do a .rename here because I know this is going to be a series, just like that. Well, I can pass this expression into Polars, I can also pass this function into pandas. So these are very similar things. And this .mean is actually giving me a scalar back, so I can't rename it. But you can see the exact same things are happening here. Well, all Polars cares about is the context. I'm using select to say, within this data frame, evaluate this expression. And the context changes depending on other contexts. And so if I actually pass in, other expressions, if I actually pass in another expression saying, give me all the values back from my original data frame, also, I want that average. Well, instead of a single value back, we actually get all of our rows back, and we've performed a transform, or the pandas equivalent of a transform here, transforming the average value back to the shape of the original data frame. If I want to do this in pandas, I would actually have to use a .assign, but I can do the same thing where I pass in my lambda function, which is the equivalent of a pandas expression, I could say, and we actually get the same result back in pandas. So context depends on the expressions present. It depends on the operation you're performing, right? Am I doing a select, right? Am I just selecting or querying columns? Or am I performing a group by ag? Because if I perform a group by ag, I can pass that same expression, which is take the values in my value column and calculate the mean. But here, we get a very different result back. Instead of seeing one row per entry in my data frame or just a single scalar product, I'm actually seeing one average value per group. And this is because Polars has fed in a slightly different context. Instead of passing in the entire data frame, it's passed in each group independently and evaluated this group for each of these, evaluate this expression for each of those groups in my Polars data frame. And you can think, since Polars knows all of the information it needs in advance, it can operate in parallel, it can operate down within its restricted computation domain, and it can optimize or perform optimizations of my code wherever it's needed. And this sounds really familiar. What else can optimize or analyze, I should say, its execution? Well, we can actually do that in SQL, or Postgres specifically, I'll be examining. If I create just a couple of tables, I have some entities and I have some categories, and they link to each other in a many-to-many fashion, and I have this table name grouping as my linkage table here. We can actually create a table and create a query to select specific things from that table. And so let's take a look at this query here. I'm selecting the names from my entities and from my linkage, and I'm performing a group by on those. And since this is a normalized database structure, right, I'm gonna have to perform a join to actually materialize all of my values that I wanna work with. And I perform my query here, and we see that I get, some rounded values per group. Well, I can actually ask Postgres to explain what it is that the query engine is actually going to do. Because really, everything that I've written here, this is not the query plan. This is just what I want it to do. My execution engine actually goes in and decides, okay, in order to accomplish that, I'm going to run this step, and this step. And what we can't do here is we cannot tell Postgres to do things in a very specific way. I might be able to hint at what way Postgres should do things, maybe by making an index here, but you can see even by creating an index, we're still performing sequential scan at every step. And maybe I can hint even harder, maybe I want to perform group by with a halving clause to really try and force Postgres to make use of that index, because I think it's the right thing to do. I think it's the fastest approach here. But you can see Postgres really hasn't changed its approach to things. And what this means is it brings up a debate. Who's right? Is Postgres right, or am I right? Is using the index going to be the fastest thing for Postgres to do in order to evaluate this query? Well, unfortunately, I don't have control over that, and I have to leave it to Postgres to make the right decisions here. So, if Polars gets to make decisions about how my queries are actually being run, and Pandas is very mechanical in that I have all the say over how my queries are actually being run, let's take a look at a few benchmarks here and see, is Polars really better? We're going to take a look at just some Python code a group by mean with Python, a group by mean with pandas, and a group by mean with polars. Let's go ahead and evaluate those. We have different cardinalities and different sizes of groups. And we can see that cardinality of 10 means I have 10 unique groups. And in those 10 unique groups, I have 10 different entities, or 100 different entities, or 1,000 different entities, or 10,000. You can see that as my cardinality increases and my group size increases, all of these evaluation times take longer. And we can obviously see that Python, I'm sorry, but you're taking almost 9 seconds to complete the hardest challenge here. That's way too slow. I can't see anything. So let's go ahead and remove the Python evaluation, and let's just focus on the polars and pandas. You can see that pandas takes longer to perform almost any calculation at any size, maybe except for this really small, right, 100-row data frame size. But for the most part, I'm not very concerned over the difference between 0.1 seconds and 0.2 seconds. For most of the analyses that I'm doing, not working with overly massive data sets, right? I'm not talking about this, and remind you that 10,000 group size by 1,000 cardinality is about 10 million rows here. So this is fairly decent sized data. I wouldn't say this is in the realm of big data by any means. But if all you're doing is desktop analyses, this is probably as big as you're going to see. So if polars is really beating pandas every time, and you can see the code that I've written is pretty much word for word almost the exact same. What about using some backend code, right? Pandas is backed completely by NumPy, and I can do a little bit of cheating here. I know that all of my groups have the same amount of records within each group, and I know the number of groups in advance. And so what I can do is I can actually convert this to a NumPy ND array, right? And then perform a reshaping operation in order to make a 10,000 by 1,000 or however many entities I have. And then my averaging operation just becomes a mean across axis equals 1. And when I perform this, we can see that NumPy absolutely beats everything. And so there is a little cheating because I made use of assumptions that both pandas and polars cannot make use of. I made use of optimizations. Well, we can see that NumPy is still going to be quite fast if you have a priori knowledge about the problem that you're working on. So let's go ahead and take a look at some slower operations in pandas. One of the most common problems that I run into is, hey, I want to run some black box function, maybe some scipy.stats function, or maybe some stats models function. I want to perform a linear regression for every group that I have in my data frame. And if I have 100 or 1,000 different groups, each with 100 different values, well, I can easily use a pandas group by apply. And this would be my naive approach. Right, I would just use group by apply. This would be the quickest thing that I could write that would produce a result. Maybe I have to wait a little bit for that result to actually materialize, but you can see it took a few seconds, but we actually got our parameters, our intercept, and our x1 and x2 betas back out. Well, let's go ahead and take a look at how long that actually took to run. Now go ahead, I executed this, I'm waiting, and we come out, almost 6.5 seconds. That took a lot. That's for 1,000 ordinary least squares regressions. Let's see if polars is any better for applying a UDF, a black box UDF, to a group. And so we can use almost the exact same syntax, group by apply, and we're applying a partial here. And let's take a look at the result. And I'll just show you the timed results instead of the actual material results because they are the same. But let's go ahead and evaluate this. We see that it runs still overall, kind of slowly, about 5 seconds to fit 1,000, but we're still faster than pandas. And so polars is doing something under the hood, maybe, to apply user-defined functions better than what pandas is doing. Now, I think a more real comparison would be if I iterated in Python over each of these groups, because pandas could be having trouble with that index-aligned concatenation after our group by apply. Right, it has to then align each of those groups back to the same ordered index that it arrived in. And so there could be an additional step that pandas is doing there that's consuming some extra time. Because as far as user-defined functions go, there's not really much that pandas isn't doing. They have layers on layers of optimizations for that, but this is still an interesting benchmark to note and requires some further investigation. Another common thing that I see in code is the use of maybe weighted or weighted statistics, grouped and weighted statistics. And so here in pandas, I can group by this grouping column. And my naive approach, well, I'm just going to use a dot apply. It feeds in my whole data frame into the function, and then I can work with those values in there. And what I can actually do here is extract my values, multiply it by my weights, and take the mean for it. But if I was smart, if I knew pandas and I knew where it was fast and where it wasn't, I would actually go ahead and perform this multiplication first and create an intermediate column. I'm paying with a little bit of memory overhead, but I am gaining 100 times speed up, right? From 0.3 seconds to 0.01 seconds. This is incredibly faster than our naive approach. And this is one of the points where it's easy to write non-efficient code in pandas, whereas in polars, if you take your naive code, and as naive as I might be, I'm using a group by, I'm using a .ag, I'm just feeding in, right, my expression, my value times my weights, and I'm taking the mean of that, and I fed it into this lazy API, faster. Polars was way faster than pandas even computing a dependent column before I was performing my group by aggregation. And we can see that with polars, it is harder, not impossible, it's harder to write less efficient code, and you have great use of this idea of polars expressions and the context that those expressions live in. And so polars has a transparency to it that you really can't find in pandas, and polars uses that to its best advantage in order to optimize the code that you are writing for you. This means that in 5 years from now, this code might even be faster than it was before. Pandas can make some of those same guarantees. It's always working to speed up group by aggregations, group by applies. But we're going to hit a ceiling at some point where pandas cannot introspect the functions that it's applying, whereas polars can. And that's what I really like about the tool. So when should I use polars? Well, I would use polars when I'm working on data pipelines that query large amounts of data and I want it to work very quickly. It can use knowledge of a schema and as well as optimizations from its expressions in order to make sure that the code that you write works well right out of the gate. I would also use polars when performing operations that can be very easily expressed via polars expressions API. If you can't express your operation in polars expressions, chances are it's going to have to materialize that data frame, pull it out of the lazy API, and then actually apply your black box function to it. Whereas in pandas, it'll do the same thing, but since there's no lazy API to pull it out of, you're not really costing anything. You can pass your data frame into as many black box functions as you want. And since most of Python's ecosystem is written to support NumPy, it has inherent support for pandas or pandas-like objects. Now, of course, polars can cast to NumPy and back, and they are actually working on improving this interface for zero copies, but I would always use pandas for that classic desktop analysis. Whenever you have messy Excel data, whenever you have multiple data files, pandas is going to be the thing that I go to because I know it is incredibly flexible. And whenever I run into a slow path or when I run into something I can't do, I know that it has a history of having workarounds and different approaches that I can take in order to come to a solution. So if you take away nothing else but this for polars, I would say to always use this expressions API and always work lazily when you are able to. Whenever your schema becomes uncertain, that's when you'll actually need to collect your data or materialize your data to perform operations right, like pivots or melts, whenever your schema is going to be changing in an unpredictable way. But that takes us to the end of our session here today. I hope you all learned something about polars, something about pandas that you can make better use of your data analysis, data manipulation, and your data pipelines and workflow. Polars is the newest tool on the block, and so I hope you adopt it into your work chains or your workflows, because although it's new, being backed by Arrow, being backed by a very strong suite of new technology that are dedicated support for data frames and tabular data analysis, it does have a bright future in my opinion. And I'm not going to say you should go ahead and abandon pandas, because pandas definitely has a place in this world too for those really uncanny data manipulation tasks that you need to accomplish. Additionally, there's going to be millions of lines of pandas code that already exist that are going to need to be updated in the future, or maybe if it's a static workflow that nobody's going to be touching in a while, you might want to convert that to something a little bit faster. But thank you all very much for attending. This has been a great session on polars, and I'm looking forward to seeing you all next time.